Hello everyone. In this video for chapter 3, we're going to talk about z-scores and the normal distribution. So we're going to talk about how you compute z-scores for individual scores and also how you use the unit normal table with z-scores. Now when you look at this graph, you can see that our mean here in the center of the distribution is 0, and we have tick marks here indicating standard deviations away from the mean. So 1 is 1 standard deviation above the mean, 2 is 2 above the mean, -1 is below the mean, and so forth. And so what you can tell is that most scores fall between -1 and +1 standard deviations of the mean, or about 68% of the scores in a distribution will fall between -1 and +1, or within 1 standard deviation of the mean. Okay? Now, if we expand to -2 and +2, if you look at within 2 standard deviations, we have about 95% of the scores between them. Right? So the vast majority of scores in a normal distribution will fall between -2 and +2, or within 2 standard deviations of the mean. Okay? If you go out to 3 standard deviations, you can see that we have 99.74% of scores, right? So underneath the entire curve, we would have 100%, all of the scores in the distribution, right? So basically, almost all of the scores are within within 3 standard deviations of the mean, 95% are within 2 standard deviations, and 68% are within 1 standard deviation of the mean. So if we look at this example here, we have a distribution drawn, and this distribution has a mean of 50 and a standard deviation of 10, right? A population mean of 50 with a population standard deviation of 10. Okay? And we want to see, you can see that 1 standard deviation above the mean then is 60, 1 below the mean is 40. And that means that 68% of our scores would be between 1 and -1 standard deviations of the mean, or between 40 and 60. Right? We have another distribution down here where we have a distribution with a mean of 25 and a standard deviation of 50. So we can see that 68% of the scores then would be within 1 standard deviation of the mean, right? So 1 standard deviation above the mean is 30, and 1 below the mean is 20, if we have a mean of 25 with a standard deviation of 5. Right? So you can see that, like in this distribution, a score of 60 on this first distribution would be very similar to a score of 30 on this second distribution, right? Because both of them would be 1 standard deviation above the mean, right? Whereas if we look at 2 below the mean, a score of 30 would be similar to a score of 15 on this distribution as well. So you can see on those previous graphs is that we're basically locating individual scores on a distribution, and what we want to know is how far any given score is from the mean. And specifically, we want to know how far it is from the mean in standard deviation units. So we can do this much more specifically by computing a z-score, rather than just looking at a distribution of scores, which really only works easily when you have whole numbers. We need to you have a formula to work with. And the formula we're using is the z formula, where we're looking at each score is an x. If you can subtract the mean from that score is your numerator, and then you divide by the standard deviation, right, little sigma. So what that means is we take a difference between a score and a mean and divide it by the standard deviation. So it puts that difference between those two values into standard deviation units. And what's nice is that this lets us compare scores from 2 entirely distributions. They can have different means and different standard deviations, but we can still make meaningful comparisons between them. Right? So a good example of this would be ACT and SAT scores. They both have very different scales, right? Different means and standard deviations, but we still want to be able to compare people's scores on those 2 different tests. Okay, for this first example, we're going to look at scores on the mathematics portion of the SAT. And we know that scores are normally distributed with a mean of 514, or the population mean mu is 514, with a standard deviation of 117. Right? And we happen to have population values here because we know the exact scores of every single person who's taken the SAT in any given year. Right? So if somebody has a score of 527, we want to know how far above the mean that person is in standard deviation units. So to do this, we compute a z-score, which is the score minus the mean divided by the standard deviation. Right? So this person's score is 527, and the mean is 514. They're above the mean, which means they have a positive z-score. So anytime somebody has a score above the mean, they're going to get a positive z-score. And then we divide it by the standard deviation, which gives us a z of 0.11. That's a positive z, which means that this person is 0.11 standard deviations above the mean. So we can also look at the z-score on the normal distribution. Right, so I have z-scores are normally distributed with a mean of 0 and a standard deviation of 1. And that's always true. If you convert every single score in a distribution into z-scores, you'll end up with a distribution with a mean of 0 and a standard deviation of 1. So right here I have the mean of 0, and then this person's z of 0.11 indicated with the line here. Okay. So I've shaded in the two sides slightly different colors to make it easier to see that line. Okay. For this next part, we're going to look at a student's score on the writing portion of the SAT. Right? So the writing and math portions have different means and standard deviations. And so we're going to compute a different z-score for the writing portion. Here our student, George, has a score of 520. The mean is 488. So he has a positive z-score because our numerator is positive. He did better than average. He has a score higher than the mean, which will give us a positive numerator. The denominator is the standard deviation. So our z here is 0.28, which indicates that his score is 0.28 higher than the mean. Right? So he's above the mean by 0.28 standard deviation units. So again, we can look at this graphically. We have the line drawn here for the score of 0.28, and the two sides are different colors just to make it easier to see that 0.28 there. Right? So you can see that that line is above the mean of 0. So if we want to figure out which subscale George did better on, we don't look at the raw scores for the writing and math tests because they have different means and standard deviations. If we want to know how well he did compared to others, we're going to compare to the means and standard deviations for each subscale. So for the writing portion, he has a z of 0.28, right, which would be about right here, and a z of 0.11 for math, which is just to the left a little bit. Right? So in this case, the further he is to the right, the more he is on the positive side of this distribution, the better he did. So he did better, right, on the writing portion than on the mathematics portion. So we often want to make more precise statements than just that, well, he did better on the writing test than the math test. We usually want to know how much better. Or another way of thinking about this is when you get standardized test scores back, it usually tells you, like, what percent of people did you do better than on a particular test? It tells you what percentile you're in. And so to answer this question, we can use something called the unit normal table. And you can find this in Appendix A in the textbook. Okay, so if you're looking, you can have to look in Appendix A, or you can look online for a unit normal table. And if you look up a score of 0.28 in the unit normal table, it's going to tell you the proportion of scores that are in the body and the proportion of scores that are in the tail. Okay, so I have this shaded in so that the body of the distribution is in red and the tail is in gray. Okay. The body of the distribution just means the area where you have more than 50% of the distribution shaded in, and the tail is the place where you have less than 50% shaded in. Okay. So since we have a line drawn here at 0.28, everything to the left, right, would be the bigger part of the distribution, right, more than 50%. Whereas everything to the right of 0.28 is the smaller part. And since that's a smaller part, we call that the tail. So when you find this value of 0.28 in Appendix A, you just have to determine then, are you looking at the body or the tail for a given question? In this case, if we want to know the percent of test takers that George did better than, we want to know what's this red section, right? This is the percentage of people he did better than. So this is the body. Right? In this case, I got 0.6103 from the table. Whereas on the mathematics test, his z-score is 0.11. And if I look that up in the z-table, I get a body of 0.54. Right? or he did better than 54.38% of people on the math test. He did better than 61.03% of people on the writing test. Okay? So he did better on the writing test than on the mathematics test. And this shows us how much better he did than other individuals who took that test. So in that case, we were looking at everyone that George did better than on the previous slide. On this slide, let's say we ask you what percent of test takers did George do worse than? Well, here, if we look at his score, if we want to know the people George did worse than, he did worse than everybody here above him, right? Everybody in blue here. So if the question asked you what percentage of test takers George did worse than, you would have looked at the tail. So people often want a simple shorthand and, well, how do I know when I look at the body or tail? There isn't a simple shorthand to decide on here. It always depends on the story, problem, right? What question you're being asked. And you have to look at the problem to decide if you're looking at scores that are higher than the one that you obtained, or if it's lower than ones you've obtained. And then based on that, you decide if you're looking at the body or tail. So it's really important to sketch out the distribution and shade in the areas you're interested in, at least when you're first starting to do this, so you can get a sense for whether or not you're looking at the body or the tail, right? The bigger part of the distribution, the body, or the smaller part of the distribution, the tail. Okay, so finally, a couple of notes about the unit normal table. One is that you can only use the unit normal table if you have a normal distribution of scores. So if you have something that's really positively skewed or negatively skewed, this table won't work. Okay? You'll find Appendix A in the textbook, and you can also use the calculator on the textbook website to find body and tails. What you'll notice is that there are no negative numbers in the table, but you can clearly get negative z-scores, right? If somebody has a z below the mean, you can get a negative z-score. And that's because the distribution is symmetrical, right? The body and tail you would get for a positive 1 is the same as you would get for a negative 1. What you do is you look up the absolute value of a z-score and then decide if you're using the body or tail just based on the context of the story, based on the problem. Okay. All right, so that is all you need in order to get started on the activities in Chapter 3.